Hello and welcome everyone to today's Calculus Notes 1.4. We're talking about continuity and one-sided limits today. So first we're going to talk about continuity at a point and on an open interval. So a function f is continuous at x equals c if there are no interruptions in the graph of f at c. So the graph is unbroken, meaning it is without holes, jumps, or gaps. And you can trace it without lifting your pencil. So that's how we can check if something is continuous. So we're going to do this on an open interval. So we're going to use the parentheses here to indicate that, which means we don't actually care what's happening at f of a. Or at f of b. So here at x equals c, this is continuous if there are no interruptions in the graph. So you can see here that I can trace my pencil without lifting it, and therefore this would be continuous. I'm going to show you a couple examples now that are not continuous. So here is one way on an interval for it to not be continuous. If there is a hole in our function, okay, so you can see right here if x equals c, it is not continuous because we have a gap or a hole. Another way is if we have something like a step function. So now on the interval a through b, we could pick a c right here. And this would not be continuous because if we tried to trace this, we would have to lift our pencil and move it down here to continue tracing it. So this is not continuous. And there's one other example I want to show you. We have a function here. So here, this function is not continuous at c, even though f of c exists, because as we trace this curve, we would have to jump down, plot that point, jump back up, and then keep going. So this is not continuous either. Okay, so in looking at this, there are three mandatory conditions necessary for f to be continuous at a point c. First off, f of c has to be defined. So looking up here, f of c was defined, so it meets that first criteria. Here, f of c was not defined, so already this one fails because f of c is undefined. Here f of c is defined, here f of c is also defined. Now the next thing we need is the limit as x approaches c of f of x exists. So this one right here, the limit exists because it's going towards the same number. Here the limit exists, but we've already said f of c is undefined, so it doesn't matter. In this case, the limit does not exist. Therefore, this cannot be continuous. In this case, our limit does exist, so this one's already met the first two criteria. But let's try the third here. Here it says the limit of f of x as x approaches c is f of c. So a direct substitution is going to work. So in this case, if I plug c in, I'm going to get the same answer as I did for my limit, making this continuous. If we check this last one right here, if I look at my limit, I would get this value, which is not the same as f of c, therefore it doesn't work. So the limit as x approaches c of f of x is not f of c, therefore this is not continuous. Okay, so again, it has to have all three of these for it to be continuous. If it fails any one of them, then it's not going to be continuous. So a function is continuous on an open interval, ab, if it is continuous at each point in the interval. Okay, so if we look at our interval, if we can pick any c, we can move this around anywhere and all three things are true, then the function is continuous on the interval. Now a function that is continuous on the entire real line is everywhere continuous. Now if f, the function, is not continuous on an open interval, then it has a discontinuity. Okay, now we can categorize these as removable and non-removable. So removable means that if we just take out one point and we redefine one of our values, f of c, then it's removable. Non-removable is not removable. So let's take a look here. So this one is not continuous. What type of discontinuity do we have? This is a removable discontinuity. Okay, and it's removable because if we remove this c and f of c, it becomes not continuous. This next one here where it steps, this is a non-removable discontinuity. Okay, even if we moved f of c up to here to connect with this portion of the graph, it still would not connect it together, and therefore it's non-removable. Okay, what do you think this last one is here? Well, we're coming up to this point, and if we would just move this point right up here, then it would be continuous. So that is a removable discontinuity. All right, let's move on and look at some examples. It says, discuss the continuity of each function. Now we can look at these things analytically as well as graphically. Analytically, we can see that this function is undefined at x equals 0. So right away, if I were to try f of 0, this would not be defined. Therefore, we know this function is not going to be continuous on the whole number line. We can also see here, we have vertical asymptote right there. And so the value we can see is going to be undefined, and the limit also doesn't exist. But it looks like everywhere else it's going to work. So what we would explain this, we would describe the continuity. So is this a removable or non-removable? Well, in this case, this is a non-removable. Discontinuity at x equals 0. All right, we'll try letter B here. Here we have x squared minus 1 over x minus 1. Now, in looking at the graph, It looks like it's a continuous straight line. But we know because of this denominator here, that it's going to be undefined at x equals 1. So right here at x equals 1, there really is a hole. Now, what kind of discontinuity is this? This is a removable discontinuity. At x equals 1. All right, for our next example here, we have two functions, and they're defined over the entire number line. So all values of x are going to work here. So we can just write that the domain is all real numbers. Now, what that tells me is that every f of c is going to be defined. Okay, because any c I plug in, I'm going to get a value. So it passes the first test of f of c being defined. Next, we would want to check about the limit. Now, we know this is a straight line here, and that's going to be continuous. And we know this curve is also going to be continuous. The only place we might wonder about is right there, okay, where this changes functions. But if we look at this, the limit as x approaches 0 of our function h of x equals, well, graphically, it equals 1. Okay, and so because the limit exists, that's great. Now, if we let x equal 0, then we're dealing with this function, and if we do h of 0, we do get 0 plus 1, which is 1. And so because the limit exists and it works by direct substitution, we know this is everywhere continuous. All right, and for our sin x, if we look at this graph here, we can see it's defined over the entire set of real numbers. So the domain is all real numbers. And if we look at this, there's nothing weird that's going to happen. There's no reason to not be able to find a limit anywhere. And so because you can do this by direct substitution every time, we know this is everywhere continuous as well. All right, we're going to move on now to one-sided limits and continuity on a closed interval. When we're talking about one-sided limits, let's just go ahead and draw our function first. And we're actually going to put a non-removable discontinuity here. We'll call that c. So here's our function f of x. And here we are at c. Now, if we want to take the limit from the left, what this is going to be, it's the limit as x approaches c from the left side. Okay. So as we trace this function from the left side, getting closer to c, what is the intended height of the function? Now, in our notation, it's very subtle. The only thing we change is put a minus right here. So that minus symbol means from the left. Now the limit from the right is just what it says. So as x approaches c from the right, what is the intended height of the function? And what the notation is going to be, it's going to have a plus sign right there, and that tells us that it's from the right. Okay, So in looking at this, the limit from the left would be this value right here, and the limit from the right would be this value up here. So let's try our example here. We have a function, the square root of 4 minus x squared. And we want to find the limit of this function as x approaches 2 from the left. So let's practice writing that in our notation. So we write the limit as x approaches 2 from the left. So the left we put minus of our function 4 minus x squared. So we can perform this graphically. So as we approach 2 from the left, right here, so x is going this way, what is our function getting closer and closer to? Well, it looks like 0. If we were to find this numerically, we could make a table of values like we did before, except now all we have to do is make sure the numbers start lower than 2 and get closer to 2. So 1.99 and then 1.999 and then 1.9999, okay, so on and so forth. So we can put this into our graphing calculator. So we have the square root 4 minus x squared. And we'll go to our table. We can see 1.99 gives me, we'll round it, 0.19. 0.06, 0.02. If that's still not good enough for you, you can just keep adding 9s. If we added 5 of them, now we see 0.006. Get out a whole bunch, and you can see that we're getting very close to 0. So we're going to say that the limit from the left side is 0. Now in our next example, we have a removable discontinuity here at x equals 0. And here we have the limit as x approaches 0 with the plus sign. So that means from the right. Okay, so here is 0. And here is from the right. So graphically, what is the height of our function intended as we get closer to 0? Well, that looks like 2 to me. If we go ahead and set up our table of values, let's see, we're getting closer to 0 from the right, so we're going to start positive and then get smaller. So 0.01, 0.001, and we could probably just do this one in our head here. So we're going to be greater than 0 here. So it's negative x plus 2, so it's really 2 minus whatever we have up here. 2 minus 0.1 is 1.9. 2 minus 0.01 is 1.99. 2 minus 0.001 is 1.999. And you can see that this is going to our value of 2. Now, why do we talk about right and left limits? Well, because it's important to see as we get close on certain sides, but this is also going to be used in the existence of a limit. So proving whether a limit exists or not. So if the limit from the left doesn't equal the limit from the right, then the limit does not exist. So the limit exists only if the limit from the right and the left are the same. And here is exactly what that's saying in symbols. So our limit equals L if and only if the limit from the left equals L and the limit from the right equals L as well. So we can see here that if we just found the limit at 2, it wouldn't exist because we have nothing from the right. In this case, we know the limit doesn't exist because coming from the left, we get a different value. And so it doesn't work. All right, anyway, moving on. What that allows us to do now is talk about continuity on a closed interval. So now we're going to be using endpoints that are there. So let's make a function. We're going to put it on a closed interval. Meaning the points are going to exist there. Okay, so this would be f of a, and then this would be f of b. So here's what it says. A function f, right here, is continuous on the closed interval ab if it is continuous on the open interval ab, so meaning all this inside stuff is continuous, which we figured out how to do on the previous page, and the limit as x approaches a from the right side equals f of a. Meaning, as we're approaching here from the right side, we can use direct substitution and find that limit of f of a. And the limit as x approaches b from the left side of f of x equals f of b. So the same type of idea. If we approach b from the left side, f of b is the same thing as our limit. Okay, so the function f is continuous from the right at a and continuous from the left at b. So that's what we would say about that function. So we can use that now to discuss the continuity of graphs that look like this. So we have the square root of 1 minus x squared on the closed interval, negative 1, 1. So we are using these x points, negative 1 and 1. So first off, is this continuous on the open interval? Okay, so if we plug negative 1, anything from negative 1 to 1 in here, we do get a value, so it is defined, and we can find all of those limits. So we know it's open on, we know it's continuous on the open interval. Now we're going to check the closed interval. So coming here from the left and from the right. So we do the limit as x approaches negative 1 from the left. Oh, is that from the left or from the right? Well, the arrow's coming from the right. So that's got to be a positive of our function 1 minus x squared. Okay, well, looking at this, our limit looks like it's 0. And we set up here that it has to equal f of a. So whatever that value is. Here it's negative 1. So if I plug negative 1 in here, what do I get? So here we have 1 minus 0. The square root of 1 minus 0 is 0. So it does indeed equal f of negative 1. So that works. It is continuous from the right. Now we're going to check that it's continuous on the left. So we're taking the limit as x goes to negative, or let's see, now we're going to this point of 1. And this is going to be from the left side, so we're going to put minus. Then our function. And we can see this is also going to 0, so we know that's the limit. And now we're going to check if we can use direct substitution Square root of 1 minus 1 squared does equal 0. So because we can use direct substitution there, this is continuous from the left. All right, let's move on. So some properties of continuity, just want to share them with you. You can tuck them away as tools to be used later. So if b is a real number and f and g are continuous at x equals c, then the following functions are also continuous at c. So if we can just have two basic functions that we know are continuous at c, then we know these things are also true to be continuous. So if we have a continuous function that we multiply by a number, we know that it's also going to be continuous at c. If we add the two functions that are continuous at c, well, that function would also be continuous at c. If we multiplied them, same thing. So continuous function at c, continuous function at c, multiply them together, we would still have a continuous function at c. It also works for a quotient, okay, as long as g of c doesn't equal 0. Okay, then this wouldn't work. Okay, so some types of functions that are continuous at every point in its domain. So these are not functions that are always continuous, but they're continuous in whatever is in the domain. And so that's going to be polynomial functions, rational functions. So notice where q of x doesn't equal 0, because that wouldn't be in the domain. Any radical function, okay, as long as it's in the domain. So again, we can't have square roots of negatives, that sort of thing. And then trigonometric, as long as x is in that domain, it's going to be continuous. So notice things like tangent, they're going to have places where it's not, x is not going to be in the domain, so it wouldn't be continuous there. But if it's in the domain, we know it's continuous. So really all you would have to check there is the f of x. All right, continuity and composition of a function, that's basically what we were talking about up here. If g is continuous at c and f is continuous at g of c, then the composite function f of g of x is continuous at c. So we want to discuss the continuity of the composite function h of x, okay, that's equal to f of g of x. So really what we want to do here is just come up and figure out what h of x is equal to. Okay, so it's f of g of x, meaning we're going to take g of x, we're going to substitute that in for x right here. Okay, so we can get something like 1 over the square root of x minus 1. Now we want to talk about the continuity, so we need to find its domain. So it's got to be on the domain. All right, so the domain of this thing, we know we can't have a negative number in here. So any value greater than 1 is going to work. And we know it can't equal 1 either, because then that would give us 0. So the domain is x is greater than 1. Now because it's rational and we have a radical, we know that it's going to be continuous at every point in its domain. So what we're going to say here is it's continuous on the interval. We'll make this open, 1, comma, infinity. All right, one last idea for today, something called the intermediate value theorem. And it states if f is continuous on the closed interval a to b, and k is any number between f of a and f of b, then there is at least one number c in the interval a to b such that f of c equals that k. Okay, so what does that mean? Let's draw a function here. And we're just going to say if this function is continuous on our closed interval a to b, that means if k is any number between f of a, right here, and f of b, so we can let k be anything between here, then there's at least one value c down here where f of c equals k. So you can see if we take k and we come across here, we would get at least one c value or if we plugged it into our function, we would get k. So what this is really saying is a continuous function will take on all values between f of a and f of b. And that's good enough to write down there. So again, it's just saying if we look between a and b, the function's going to take on all the possible values between f of a and f of b. So going in here, we hit every single one along the way. Okay, so if the function's continuous, we know that's true. So here's how we can apply it. It says verify that the intermediate value theorem applies to the indicated interval, and then find the value of c guaranteed by the theorem. And we want to add on one other question here. We want to show that f of x has a 0 in the interval. Okay, so first off, to verify that the intermediate value theorem applies, it means that f has to be continuous on the interval. So on the interval 0 to 1, is this function continuous? Well, it's polynomial, and 0 to 1 is defined on the whole way. So we do know that this function is continuous. And now we want to talk about this interval idea. So what we're going to do is we have our interval 0 to 1, and we need to substitute that into our function. So we're going to find what's going on at f of 0, and we're going to find out what's going on at f of 1. Okay? And notice these two values here are going to correspond to these two values right here. Okay? So that's what we're finding right now. So f of 0, 0 cubed plus 2 times 0 minus 1. So that just equals negative 1. Then f of 1 would be 1 cubed plus 2 times 1 minus 1. And that equals 2. So on this interval, 0 to 1, we know that it goes from negative 1 to 2. So graphically, let's just kind of see what happens here. So here is our interval going from 0 to 1. And it's saying that this function is continuous, and it goes from negative 1 right here all the way up to 2 up here. So this is sort of like putting pieces of the puzzle together without actually seeing the picture. So the question is, show that f of x has a 0 in the interval. Okay, so if we start here at negative 1 and we end here at positive 2, and we know this function is continuous, okay, what does the intermediate value theorem tell us about the function? Well, it tells us that it equals every possible number between negative 1 and 2. So at some point along the line, will the function equal 0? Okay, so will the function ever equal 0? Will it ever cross this line? Well, yes, it has to. Without even knowing what this function looks like, okay, we know it's going to cross right there. So how are you going to write that mathematically? You're going to do this. You're going to write f of 0, so our left interval, is less than f of c is less than f of 1, which is our right interval. So our f of c equaling 0 has to exist on that interval. So we just write a0 exists. Now, if we want to find the value of c guaranteed by the theorem, we know it exists. So we know the 0 exists. Let's go ahead and find it. So we want to know, where does that function equal 0? Now this is a cubic, and it's not going to be so easy, because even if we factor this, even if we add the 1, we get something like this. All right, we really have no methods for solving this. So what we can do, since it's asking us to find it, is we can use our calculator to find that 0. Okay, so go ahead and take out your calculators. And we want to put in the function x cubed plus 2x minus 1. I'm going to go ahead and hit graph. Okay. And you can kind of see we got kind of close. And you can see between 0 and 1 that it is continuous right there, and it does cross the x-axis. Now to be able to find the 0 on your calculator, you're going to go second and calculate. So second calc. And then you're going to select 2, which is 0. Now it says, what's the left bound? So we want to go to the left of the 0, and so we're already there. And then to the right bound, just anywhere to the right of it. And then it asks us to guess. So we're just going to put our cursor close, and hit enter. And here it approximated our 0 at 0.453. So here x is approximately 0.453. So our value of C, which is guaranteed by the mean value theorem, is 0.53 approximately. All right, there's just a little example on the back that I want you to go ahead and try. And just understanding whether you get the limits and the discontinuities, and you want to discuss them using everything that we talked about in the lesson today. Bring this to class next time and we'll go over it. All right, that's been Calculus Notes 1.4. Thanks for watching and we'll see you in class.